Hiya, I'm Barnaby. I'm the team lead for StratZed this year for the mission Kaleidoscope for the Mach-24 competition. This is our preliminary design review. If you have any questions, please contact me at the email address on screen. So, our mission statement is split into a primary, a secondary, and a tertiary mission. Our primaries are to launch a 1 kilogram CANSAT to 3 kilometers with less than 5,120 newton seconds of impulse. Our second primary mission is to use a two-stage recovery system on the launch vehicle to minimize drift from the launch site. Our secondary missions will be to transmit video from the launch vehicle to the ground during flight and to measure the speed of sound during CANSAT descent to determine its current altitude. Finally, our tertiary missions are to use recycled plastics in 3D printed components and non-structural, to relay live telemetry and video feeds to a Twitch stream, and to use edge machine learning to analyze video from the launch vehicle to help us learn more about flexural torsion flutter. So here's a brief overview of the timeline of our mission. About 5 minutes before launch, we'll establish a telemetry link between the launch vehicle and the ground station, as well as a payload and the ground station. Additionally, establishing a video link between the launch vehicle and the ground station. At T0, our motor will ignite, and approximately 1.75 seconds later, it will burn out. At T plus 22 seconds, we expect to hit our apogee of 3,300 meters. At apogee, we will fire an ejection charge to eject our drogue parachute and our CANSAT. Approximately 10 seconds before landing, we expect to lose video from the launch vehicle. However, we expect to maintain a telemetry connection until recovery. While this has all been happening, the CANSAT has been descending and using an acoustic altitude sensing system to detect its current altitude. Daniel will go into more detail on how this works later on, and we expect this to land about 3 minutes after launch. The following day, we will process the data from both, going over to a breakdown of who the team are. We have myself, who's the team lead. We have Jamie, our mechanical sub-team lead. Daniel, our electrical team lead. Kyle is our coding team lead, and Sammy is our treasurer. This year, we have managed to get an academic advisor. This is Dr. Massimiliano Basile. Breaking down who the mechanical team is, we have Matthew and Pablo, who I'm sure a lot of you have met before. We have Joseph and Alice, our new first year intake. We have Connor, and we have Isaac. Anyway, our electrical team is Jakob and Kia, and our coding team is Callum and Sean. I'll now pass you on to Jamie to discuss how the launch vehicle will work mechanically.
Thank you, Barnaby. I will now take you through an overview of our current working assembly for the launch vehicle. Due to significant integration issues last year, we have moved the avionics bay into a coupler tube at the fore end of the rocket. This will allow us easier access to be changing batteries and for stacking the rocket on launch day. Contained within the AV bay, there would be a camera with a mirror to allow filming the exterior of the rocket with a significantly reduced profile. Taking you through our motor selection process, we have chosen a Pro 54 6-grain White Thunder, as this brought our vehicle to the highest altitude with our current simulations. Our best alternative would be the K711. The vehicle will be mostly constructed of fiberglass with fins made from water jet cut sheets and COTS tubes for our airframe. Parts taking significantly less load will be 3D printed. This will include some sleds for our electronics within the avionics bay. Our recovery systems will be the first ejection will be going off at apogee, with that releasing our drogue chute and CANSAT from the aft body tube. The event 2 will then release the main chute from the nose cone at around 300 meters. I will now pass you on to Daniel.
I'm going to now talk to you a bit more about the electronic recovery systems. We have 2 COTS flight computers on board, an X-Timer Quark and an Easy Mini. These are set up in a redundant configuration with 2 ejection canisters, one for drogue, one for main, and each canister having 2 igniters. So both the Easy Mini and X-Timer can fire each as needed. We will be using these as they are both flight proven in our previous IRW launch, and we will be retesting them in the lead up to our launch. We would also like to test the pyrotechnic capabilities of our SRAD computer Firefly, as we realize we can't use this to control any real pyro charges. This will be in a completely isolated setup. We'll have 2 igniters surrounded in Nomex, and then further surrounded in a solid plastic shell, so there's absolutely no chance of this affecting anything outside of it. Moving on to the telemetry, our main telemetry links will be the Firefly 1.1, which is our SRAD board, and the Octo 4C Plus for our live video streaming. We will be transmitting on our Fireflies the GPS, altitude, orientation, and payload telemetry. This will be on 869 megahertz with a 100 milliwatt transmit frequency. We will also have the Octo 4C Plus transmitting our live video stream. This is going to be on 2.4 gigahertz at 100 milliwatts. Our flight computers that are COTS do not have any telemetry, so that's not required. The frequencies we are using are license exempt under IR 2030, with 869 having a 500 milliwatt max and 2.4 having a 100 milliwatt max. And airborne use is permitted on both. Just an aside, we are also developing the StratSat SpaceLink app, as well as the ability to visualize launch telemetry live during flights. It will also include a recovery mode, which will show the rocket and payload's last location due to received packets, and also the wind drift using local winds. This will allow us to slightly improve our ability to recover with a more accurate predicted landing zone. This will be available to anyone using iOS or Android. Moving on to our sensing systems. Our main payload this year on the CanSat is our acoustic altitude measurement system. This uses one speaker and two microphones. We will measure the time taken for the signal to go from one microphone to the other and use this to get the speed of sound, and through some temperature and humidity corrections, we'll be able to get a good pressure and thus altitude from this. We're not expecting it to be super precise, but we are expecting a good difference and a good result between 0 and apogee. Our main other system is our live stream video. This is going from our camera that is looking at the fin flutter, going through to an Octo 4C Plus. We are transmitting the video feed over a LoRa 2.4 gigahertz link, which will be received by our tracking ground station. This ground station will be tracking on the GPS data transmitted on our low-speed 869 megahertz link and use that to predict and follow the rocket during flight. As the power limits are so low and the data rate so high, we'll be using a high gain antenna, so precision and pointing will be quite important. This data will be fed from the tracking ground station into a Raspberry Pi, and then further on into a laptop to be streamed live on our Twitch stream. So just going over a bit about our refinements from last year. So this is Firefly 1.1. We have added a real-time clock to synchronize our radios instead of our previous GPS implementation. We have fixed the performance degradation caused by poor clock power filtering, and we've also consolidated the GPS onto the main board as we had some issues with the external board last year. We've also improved clearances for mounting and added redundant pressure sensors, one on the front and one on the back. I'll now be handing you over to Jamie, who will talk to you a bit more about the mechanical structure.
Thank you, Daniel. I will now take you through the mechanical structure of our can. There will be two chambers contained within the can. One will contain the majority of our electronics, and the other acoustic chamber will contain the ultrasonic sensors. The can will be constructed of PLA+, and the FEA will be completed on this to ensure that it's strong enough to withstand the forces at launch. And once we have a 3D printed prototype, we'll also do some load testing. Within the can, the electronics will be securely mounted to a sled to ensure that everything stays connected through the significant G-forces at launch. I'll now pass you on to Sammy.
Thank you, Jamie. So this is a risk assessment that we have come up with ourselves. It's mainly things that we're going to face on the day of the launch itself, but it's also got some factors to do with construction and testing. And the department requires us as a society to complete some risk assessments as well, so we've done those as well. So we're really taking every precaution that we can to ensure safety during the process. Here we have our budgeting breakdown. So right now we're projecting that our cost is going to come to around £3,000, and this is split mainly between three sections: the mechanical team, the electrical team, and some admin fees as well. So I've tried to break it down as best as I can. Our main fee for admin is the entry fee itself, and then we've got a couple of costs for transport, launch, and then some more admin fees that we need to take care of. Our electrical team, I've split between the Firefly computer and I've kind of blanketed the rest of the components because there are far too many of them. And with the mechanical team, I've got our launch vehicle itself, the motor, and the body tube, which are going to be our main expenditures there. All the known admin fees we have been accounted for here, and we're awaiting some sponsorship outcomes so we can try and take our current budget to our projected cost. Because currently from the uni we've got about £2,600, and then from sponsorships we have a further 100, which has taken our current budget to about 2,700. But say we don't get the sponsorships, we can also look to the University Society's exec grant. So there are a couple of possibilities there. So I'll now pass back to Barnaby, and he will take you over the timeline.
Thank you very much, Stanley. I will now break you down on our current timeline for the project. So we're now sitting at the beginning of February. We're expecting our mechanical design to keep going until after our exam break in May, with its construction expected to start just after the exam period at the middle of May. The electronics team has a bit more of a breakdown. They have their first expansion board on track to be completed by the end of this month, and their payload board and radio boards to be completed by the end of March. So our coding team is expecting to continue modifying the firmware all the way up to launch day, with extensive testing happening as the firmware is updated. So between the preliminary and critical design reviews, we have a few steps we have in mind. We need to finish the CAD of payload, launch vehicle, and our expansion boards. We need to finalize these designs, ideally before the critical design review. We will start making some prototypes of key components, including the camset and boat tail mechanisms. We will complete some more in-depth manufacture plans and relevant risk assessments when necessary, and we'll complete a full testing plan before the critical design review. Before I finish off here, I'd like to thank our sponsors, Recol, Northern Laser Limited, the University of Strathclyde Alumni Fund, RS Components, ANSYS, Altium, and JLC PCB. Thank you very much for listening.